Jörgen, the floor is all yours.
Thank you so much, Peter, and thank you all for being here. I think it's such a great initiative, this LEG webinars, that we can meet regularly and discuss research topics of common interest. And I hope this will interest you, although it's not directly on learning or evolution, it's indirectly on evolution and learning. And it is a project that I've been working on for some years, actually, with Klaus Ritzberger, Royal Holloway, and Peter Wickman, who is now in Stockholm, who was a postdoc at Toulouse. So if I look back and in the broad perspective first, for me, game theory, my work in game theory is meant to be useful for applications. I think it's, of course, intriguing and fun to explore theoretical properties and concepts and so on, for sure. But the ultimate goal is to have something to provide for application, to have it useful, mostly in economics in my case, but also sometimes in biology, political science, and other fields. And then I've been embarrassed sometimes when I meet people who work on applied work or applied theory, let's say, in political science or in economics and biology, that there is such a bunch of tools with different properties. And it will depend rather much on what they want to do, what is the goal, of course, and so on. That's normal, but also that we have different tools and they will give different answers. And it depends also on sometimes on details that shouldn't matter, hopefully, but they do. And we would like to have something that, one can represent the game in this way or that way, extensive form, different extensive forms, normal or strategic forms, and so on, and have different tools for those. And so it has been now what I've been looking for and worked on now with Klaus and Peter is to look for something that is structurally appealing, that has invariance properties, robustness properties, and agrees with basic principles of what one could call rational play in games. And it should be connected with evolution and learning in games, something that's learnable. And another aspect that I would add on to this is actually computability. So it should be something that one could use, not only simple examples. I will give some simple examples today, but actually somewhat more complicated examples, so one could see what it brings in simple applied game theory. And this, I think, has been a problem with evolutionary game theory in particular, and also, but also non-cooperative game theory. Sometimes researchers are able to produce very important and powerful concepts and methods, and then when illustrating them, one usually uses very simple examples. And then some people who work in applications, economics or other fields, they feel, well, is that all you can really say? Is something about a 2x2 coordination game or something? But they have in mind, they would like to know what happens if there are 5 players and there are a few stages in the game or things like that. And usually we say, well, that's something one has to calculate, and we don't have things ready. And so these are aspects. And also I'm trained, basically I'm trained as a physicist. I started out in physics and applied mathematics. And then I think a little bit like an engineer in some sense. I want to talk about things that are observable, where one could falsify things, so that the objects should be things that one could actually, in principle, observe, at least in laboratories or in the field and so on. And then when we work on standard solution concepts in game theory, we work on non-observables usually, namely strategy profiles. In some simple games, of course, one can see, from the data what strategies people have used, but many times one cannot. One can only see what they did on the path of play. And that is what we really care about when we want to use game theory, that what will be the outcomes. And by outcomes, I mean 2 things actually, as you will see. So our basic notion of outcome here is a probability distribution of the plays of a finite extensive form games. You see what happens along the way as people play, what actions did they take and did not take, and where did they end up, and what were the gains or losses and rewards, and what are the, and so on. So these are the outcomes. One can also talk, of course, in a normal form representation where one cannot really see these things. One can look at the outcomes, but then it will be payoff outcomes. And that's a different concept, of course, because it could be that there are different outcomes in some extensive form, non-generic, but the same payoff outcome. So this one has to be careful with, but I think it's useful to think about that I would like to have solutions that are defined in terms of outcomes, and the solution concept should have good invariance and robustness properties. And I'm not, this is not the first time this question has been raised, and some of you have contributed already to this. So we just we try to add something to that edifice of work, but slightly different approach. So when I mean this with invariance, one can mean different things with invariance, of course, but what I have in mind is really that it shouldn't matter so much how we write it up, the game, hopefully, just like a roadmap. We don't want to have all the details of a road with every house and tree. That's not useful for driving or walking or hiking, but capturing the essentials. And that's also how one does in applied work, right? One doesn't write down games that are meant to capture every aspect of the interaction. That's a daunting task that is not very useful. And usually the researcher has to select some aspects which he or she finds important and then to emphasize those and let games here help to clarify those aspects. Now, robustness can also mean many different things. And one form of robustness is that players might make mistakes. They might be uncertain about intentions and actions by others and so on. But one can also by robustness mean, and that we will mean by robustness here also, not only that, but also that sometimes we as analysts, we have tried to specify a game empirically, and in particular the payoffs. So maybe we have agreed that there is an extensive form that is appropriate for the situation, and then we want to, specify what are now the payoffs, and usually we don't know them, but we can sometimes try to elicit them, and that's done in laboratories and so on, or make hypotheses about them. So if we are not super sure about the exact specification of the payoffs, ideally the solutions should be somewhat robust to that. Now, yet another aspect is consistence with some form of backward induction. So even maybe we are given, or we are writing up an extensive form game. Maybe we write a normal form that we have derived from an extensive form, maybe. But some form of backward induction, I think, makes sense in most applications, even with weaker rationality assumptions than we usually make. However, there is also a question about backward induction, and I will come back to that. In some games, we assume implicitly in our solution concept some kind of persistence of rationality, that it is as if players should maintain hypotheses along the play in a tree, that others are acting rationally in the future. And this is something I will take up also, that we don't have to make really that. I think we can be agnostic about that if we look at outcomes. And finally, as I mentioned, computability. If the solution concept is such that it lends itself to algorithmic work to compete and solve the game, at least in games of moderate size. Now, there are different roads to approach this topic. And if you excuse me, I will close my office door because people are speaking outside. It's just like. So the way I view game theory, and I mean, can you hear me? Am I okay? Yep. So the way I view it is a little bit game theory. It is that I think of it as what we work with are mathematical objects. I mean, normal form games, extensive form games, and so on, and solution concepts for those, and other concepts. And I think it is important that those are the objects we work with, like a sculptor or painter works with stone or with oil on a canvas. Then we have interpretations. So that's a different thing. So then when we work, say, applications in economics, we might want to think in terms of rationality of the actors, or in evolution, something like natural selection or learning, and so on. But these are interpretations, and then they will inspire us how we look at it. But then these interpretations are, of course, different. And what happens when you apply solution concepts that are adapted to either one or the other, that sometimes the predictions will agree, but not always. And one example here is given here, a very simple example, that some Nash equilibria do not fare very well in evolutionary game theory, but they survive in non-cooperative game theory, even the most stringent refinements. And here's a little coordination game with positive numbers A, B, C, D. And this game then has 3 equilibria, 2 strict equilibria, and 1 mixed. And I would argue that the mixed is not a robust prediction for most applications of play, but yet it survives many criteria that we have. And in evolutionary dynamics or so on, it will not survive. The small perturbations will lead it away. And I think most learning models will do the same. Now, let's then look at invariance, robustness, backward induction, and computability, and consider some of the familiar concepts we have in our toolbox. So Nash equilibrium has quite nice invariance properties and also computability properties. So that's an advantage, and it's very elegant. I think it's a beautiful concept. But as we well know, it lacks robustness. And also, as we also well know, it does not imply backward induction, but it can allow for many things that don't look convincing in extensive form games. So then one can turn to extensive form concepts and look at the whole range of concepts there. But what I would can talk about subgame perfection, extensive form perfection, and sequential equilibrium to start with. But then it is also known that these are sensitive to arguably inessential modifications of the extensive form. If you think of a 3-way choice as first a binary choice and then another binary choice, or things like that. And then they will have different predictions. So this makes it sensitive to things that we might want to think, at least when we apply them to what we think of as some rational, in some sense, decision makers. Of course, it matters here. If we think of applying the theory to boundedly rational individuals such as ourselves, who have difficulties to handle menus and want to avoid some options and so on, that's a different matter. And that's not the topic here, really. The topic here is more classical game theory, in the sense that what would be, if we think of rationality as a basic paradigm, and I think of, when I say rationality, I think of Bayesian rationality in the sense of Savage or something like that. So that people behave as if we could explain their behavior as if they had some value function that they evaluate the expected value of in terms of some subjective probabilities that agree with information that they have, something like that. I'm not so precise here, I know, but I think these are interpretations, and I'm focusing here more on the mathematical structure. So these concepts then do a job with backward induction and represent that, but they are sensitive to those things, so they are not invariant in a strong way. And then one can go to the normal form, and also there Reinhard-Zelten appeared on both these agendas. And one can obtain good robustness properties in some sense, namely with respect to uncertainty about one's own and others' trembles and mistakes and so on. But these lack invariance. So one could say that if one changed the game by adding a strictly dominated strategy and so on, then that changes the prediction and things like that. So I think they are, by and large, lacking in invariance. Okay, and then we have strategic stability as developed by Kohlberg-Mertens and then Mertens. And it has a lot of robustness and invariance properties. But I think it is quite hard to compute. Usually when one teaches this, it's very pretty with their axioms, it has many properties, and then, when it comes to applying it, it's a really hard work. And I would think also it doesn't really capture, I think, what we are trying to look for here. And for example, this mixed equilibrium in the simple coordination game, it admits, for example, and I think that is not capturing, I think, what we would like to have for prediction of real life interactions. And then there is a concept of persistence by Kala and Sammet in the 1980s. that does reject a mixed equilibrium in, for example, this coordination game, as does evolution stability considerations and evolution dynamics. But again, one can show that this lacks some invariance properties that seem desirable. So it is not exactly fitting what we are looking for here. So we will look for something else then, try to combine some tools and make some progress. And as we all know, if one writes up a long list of desiderata, one can rather quickly come to the conclusion there is no point valued or singleton valued solution concept that meets this. So one would have to work with set valued solutions. And what I will suggest is a combination of a set valued and an outcome valued solution concept. And what we will call these sets, we will call them minimal game blocks, and we will call the outcomes solid outcomes. And I will then try to demonstrate invariance and robustness and backward induction properties that these have, and also show that it has a connection with evolution selective dynamics, asymptotic stability in those, and also actually with the concept of sustainability, as I will mention briefly at the end, a concept that was suggested by Meyerson many years ago, and then developed by Hofbauer with a conjecture, and then it was worked out by von Stengel and others, and now most recently last year by Govindan, Laraki, and Pal. So I will be brief on that, but I will mention it. Okay, so this is what I will talk about. And then I just want to mention 50 or many, I mean, there are so many references, I will not talk about them, of course, and you know many of them, and some of you are here present. So for example, Dietis and Joseph and Christoph's paper is a paper in this spirit, I would say, and we differ a bit there, but they are not in spirit, I think, rather related. I did work with Kaushik Basu many years ago on what are called curve sets, and then what we will use some of the mathematical work of others, and there is also Stefano de Michelis and co-authors, including Klaus, who is in this paper also about index theory and stability, and we will use index theory here. And then there's another piece which I think is important for us when you talk about the invariance across different representations of a game, the paper by Susan Elms and Phil Rennie, where they look at the Thompson transformation of extensive form games that leave the reduced normal form unchanged. So if one deem that these should be inessential transformations that they discuss and Thompson discussed. So they are a little bit different because they wanted to preserve perfect recall, which Thompson did not. So if one looks at those and say that, well, rational players, it shouldn't matter if we vary the game in this way or the other, then it says that it should depend on the reduced normal form. Okay, here is a paper I mentioned on sustainable equilibrium, came out last year in JET. We will talk about regular equilibria and so on, and that's Harsan who started that, followed up by Erik van Damme. And I mentioned some, about outside option games and forward induction and so on, and stability. I will touch upon that also. And here are some references that we have talked about already. And of course, Kuhn's work is fundamental, like extensive form. I mentioned here David Lewis' book on convention, philosophical study, which I think it's a beautiful book. It's a verbal book, but it deals with what one could mean by conventions and also common knowledge. And it's actually a slightly different concept than Aumann's notion of common knowledge. But I think it's I think of games sometimes that they should represent something that if the game was embedded in a population setting where people had some experience from playing it or others playing it, who were familiar with the game, our solutions should not disagree then with what they are likely to do. Mayles, Samuelson, and Swinkles worked on extensive form reasoning in normal form games, which is then related to what we will do because we need to connect between these two representations. And McLennan has, of course, is the master of fixed point theory and index theory. And then we have Martens and Meyerson, and I wrote a paper some years ago with Roger Meyerson about related topics, and so there is some connection with that also, what we will talk about here, but the approach here is different. It's more computable and has more explicit, we could derive more explicit invariance properties. Also, Peter Wikman, who is a co-author, has a paper. He has one published paper on something he called Nash blocks by himself, which is related to some of the things we do here. And he has also this one together on a working paper where they look at tenable strategy blocks in the sense that Myerson and I developed, and evolution stability, actually. So there are relations there also. Well, we have Klaus' earlier work is very important for us here. Rubinstein's discussion of what is a strategy and the meaning of a strategy and so on, and outcomes that I think is related to our spirit also. And Zelton, of course, and Swingtals and so forth. And then there are other people. Olivier Tercieux has done beautiful work on set value solutions. And Van Damme's contributions, I think, are extraordinarily important. And we will use one of his, I think, most beautiful results here. And here's Van Gemde and so on index and stability and things like that. And my colleague, and here in Stockholm, Mark Fornevelt, has also made contributions. So let me now leave that and talk about what do we do, and then we can come back if you like to discussion. Is there any question you would like to raise now? So you please do that. I mean, I'm happy to take a break.
I have a quick question, if you, since
sure.
you give the opportunity. So just for out of curiosity, you didn't mention the Neumann-Morgenstern-Sable set. Is there a reason? Is this is what you do completely different in spirit? I mean, I don't know what this solution concept, which of these desiderata it would satisfy.
This is quite different. So it's quite different from what they do, but you are right. I mean, they were striving for something important there, of course, but with their machinery. So it might be worthwhile to explore it again, since we see, is there anything there we can learn when we do our non-cooperative games here? But this is not closely related to that.
Got it. Thank you.
Thank you. Okay, so let's get into some of the nitty-gritty here. Standard notation that we will look at finite normal form games and also finite extensive form games. And I just use capital I for the set of players, little I, and there are finitely many, n of them. And each of them has the pure strategy set that is finite, Si, and the product set is a set of pure strategy profiles. And then we imagine that there is a mapping to Rn from those strategy profiles, so that this vector is the vector of payoffs, which represent their preferences. And of course, we will talk about extensions to mixed strategies and extend the payoff functions to expected values with respect to mixed strategy profiles. And then I will talk also about extensive form games and behavior strategies, and use also then Kuhn's theorem, of course. We will assume perfect recall. And some observations before I start I will now try to set up the definitions in a few pages, and I start by just recalling some things. That if we take a finite game now, the set of Nash equilibria is very pretty mathematically semi-algebraic, so it consists of polynomial inequalities, and that they define finitely many closed and connected components. So we can always talk about these Nash equilibrium components, and they are well behaved. I don't say they're easy to find, but they are well behaved mathematically. Now, if you look at those, one can then apply index theory. And here the expert is Klaus, among us. He has worked with De Michelis, also Stefano, on this. And the index is a way to give integer values to fixed points, and essentially try to capture how robust they are with respect to perturbations of the functions involved or correspondences involved. And let me illustrate it by a simple picture. So, so if you see this graph here, it's just a continuous function like an S, the solid red, mapping the unit interval to itself. And we may be interested in fixed points. So these are the intersections with the diagonal. And you can see here 3. And you see that these intersections are transversal. So it actually hits with an angle, and it comes from upside to down, under, and then from below to above, and then from above. So in this case, one would say that it has the index of the first intersection, the lowest value of x, +1, it comes from above. It's -1, the middle one, because it comes from below, and then it's +1. And as we know from cobweb dynamics and so on, when we look at such functions, we get convergence and stability usually for those that have here index +1, right? So it would be unstable, usually iterations we do in economic models and so on. Now, this is the basic insight, and this can be then generalized to arbitrary dimension. And just to point out the possibility of zero index, look at the dashed line. That's another continuous curve, which has also, it's meant to have two fixed points, two intersections. One is when it touches, just barely touches upon the diagonal at the lower value, the dashed line. So let's imagine that's just 1 point. It just dashes there. And the other one, it intersects, it's transversal. Now, if we would perturb that continuous function slightly, it might be that then that the lower point, the low x value around 0.35 or something, would vanish, because that curve could lift upwards a little bit and it would just go away, but not the upper one. And here the index would be 0 on the one which is actually the tangent is parallel to the diagonal, and 1 for the transversal one. Okay, so usually +1 is a necessary condition for stability and reasonable dynamics in all kinds of models. One can also think of whole components that are connected. Suppose that one curve follows the diagonal for some time and then takes off. One can give index to those also. And one can do the same thing then for Nash equilibria in games, finite games, and one can do the same thing for Nash equilibrium components. Now, no matter how one does this, if one looks at a finite game, then the polyhedron of mixed strategy profiles, so the strategy space in terms of mixed strategies for everybody, is a convex set, and it has an Euler characteristic of +1. And according to deeper results in Hopf-Poincaré theorem in mathematics, it's necessary that the index agrees with the Euler characteristic, so that for stability, so that so this is the case. And then also, if one looks at these games, and one would sum up the index in all of these components, that sum is always +1 in any finite game. So we have some basic structure here, and these are things. The index is something one can compute with an engineering task to find. Not always easy, but there are algorithms for that. So this is something one can use, and it has been used a lot in different fields, in engineering and many other fields. Okay, so that's one thing. Now I go into our terminology. So what when we say a block, we mean a strategy block. What we mean is a product set. So we look at each player and we say, here is a subset, not empty, of your strategy set of pure strategies. It might be the full set or some subset, and we call that product. And when we focus on this on those for everybody, so only on the subsets for everybody, we call that a block or a strategy block. And this is terminology that Myerson and I used to have worked, and some of you have worked on these things, in different contexts. So one ask myself, can we restrict attention to some subset for each player? Now we introduce the terminology here of saying that such a block respects equilibrium components. If it's the case that if you look at an equilibrium Nash equilibrium component and you look at two different Nash equilibria, okay, then they should all have support in the same block. So it doesn't intersect. This block construction does not cut any component in parts. So if one equilibrium is in there, then the others are also in one block. So we can say that the component belongs to a block or not. Okay. So that is what we mean by respect equilibrium components. And of course, that is true for the full strategy space, that it respects that. Now, then we say that the game block, by that we mean any block that respects equilibrium components and is such that if we would count the index for those components that are in it, the sum is +1. So that's the same thing that holds for the full game. And that is something which makes it as a candidate for something that can be stable dynamically and so forth. And it agrees with the standard setup for finite games. And then we say that the game block is minimal if it does not properly contain any other game block. And the idea why look for minimality, one reason is precision. We want to make precise predictions. Another one is that if we imagine some kind of process going on there, which we don't model, as people adapt their behavior and so on, if things are happening, wiggling around a little bit in practice, and if you have a game block which contains properly another game block, it could happen then that population will move into that game block and maybe not get out, and so on. So it seems that for long run predictions, one can use minimal game blocks as useful predictors. And that is in line, of course, with most of natural science and so on. We want to make predictions that are precise and that we can refute, that they're falsifiable. And of course, every finite game has at least one minimal game block, because the full strategy space is a game block. And if you find a smaller one inside it, then a game block, then there are finitely many sub blocks, and either there's no sub block that is a game block, or there are some, and then we can look at one of those, and so on. So this is trivially satisfied, right? So don't have to worry about existence of minimal game blocks. And moreover, one can show that they actually lean, so they take away strategies that are not used in any Nash equilibrium in the game with support in the block. So they kind of shave off or take away strategies. Now, as I said, we will combine set-valued ideas with outcome-valued ideas. And now I turn to extensive form games. So what you will notice here, and that makes it a bit maybe complicated to talk about it, but it's not a basic idea. Is simple, that we think of some real life situation, and the researcher could write up an extensive form game to represent it, and we can work on that, and then we can look at its normal form representation or reduced normal form representation. It could also be that we are given a normal form. So what I said so far is that suppose we have a normal form, and then we can define what we mean by a minimal game block. Now I say suppose we have some extensive form that we look at, and then we can look at its normal form, of course. So if I look now at the extensive form, then we follow Krebs and Wilson in their terminology, and by an outcome, we mean a probability distribution over its place. Now there are finitely many plays. Each play goes from the root of the tree to some end node, right? There are finitely many of those. And when you play some strategy profile, if people use strategies and play the game, whatever they do, they can play the game in any way they like. But at the end of the day, exactly one of the plays will be realized whenever they play it, whether they use mixed strategies, pure strategies, behavior strategies. So if one looks at the Nash equilibrium of the game, one can then calculate, what would be the probability distribution if this Nash equilibrium is played over the plays of the game. And I think these are candidates for what we think are things we can observe in principle. Of course, we cannot observe full distribution if we just see people playing a game once. We can see some point that we would presume then should be in the support of what we have as a theory. But if it's possible to make repeated observations or laboratory studies and so on, and one can look at distributions of behavior, then one can, in principle, approach this. We might not know the full strategies because people might have plans for doing things that they never have to do. So if I take a Nash equilibrium component now of the normal form representation of this extensive form game, then we can look at those outcomes that are induced over the game tree by those strategy profiles that live in the components. Those are the Nash equilibria in that component. Now I can define then this last part of the concept we have, namely that start with the finite extensive form game with perfect recall, and then we say that the solid outcome set is any set of outcomes that is generated from some equilibrium component with non-zero index with support in a minimal game block. So the idea here is to say, okay, we look in minimal game blocks, first of all. Then we say we don't look at components with zero index. This was the tangency case of the dashed curve, if you remember, when I draw the S curve. We focus on those that have non-zero index. They can have -1 or +1. We don't rule out -1 here, and you will see later on why. But it should be non-zero, because non-zero is enough for robustness with respect to the representation of the game and the payoffs. Now, if such an outcome set that is emanating from a component is a singleton, then we call it a solid outcome. Okay, so a solid outcome is not a point in a set, solid outcome set, but we use the terminology solid outcome means it's a singleton solid outcome set. And then we know then, as you know from Krebs and Wilson, that we can actually use this and obtain those in generic extensive form games. So let me state this here, some facts. First of all, every finite extensive form game with perfect recall has at least one solid outcome set. That's easy to see. And then those outcome sets are always close connected sets. So these are sets of probability distributions, so they hang together. But one can be sure that there exists at least one solid outcome. So it's a singleton for a component in every generic finite extensive form game. And generic here means that we can vary payoffs for a fixed extensive form. So the form is here fixed, we don't vary that, and then we can change those. And this is then Krebs and Wilson, right? So what it says, in other words, it says that the outcome mapping is constant on the components. There are finitely many outcomes in a generic extensive form game. And we think this is a relevant class of games to study for application. Because if we would do serious empirical work, strict, really true indifferences would be rather rare. People would have some preference over something and so on. So we say that that would be natural to say that that is a relevant class. Of course, ideally, we would like to say, and we say some things about all extensive form games, but I think that to be able to say some useful things about generic extensive form games in this sense is also helpful because it's empirically relevant. Which is not to say generic normal form, because that is a much stronger concept. So these that are generic in the extensive form game, they might be non-generic in the normal form. So this is a permissive concept. Okay, so if I go through some examples now, and then we go back to theory again, is that okay? Are you doing okay? Are you hanging in there, or you find it boring, or how do you feel? Is it okay? Okay, so let me do rather quickly some examples. So start by the simplest possible. So let's look at 2x2 games. Suppose that these numbers A and A prime and so on are all positive. So that's a coordination game. We have two strict equilibria, and these each have index 1 + 1. And the mixed has index -1, so it's not 0. But that mixed one is strategically stable. So it's accepted by perfection and properness and everything like that. But not here. So in this case, there are only two singleton minimal game blocks, namely the singletons associated with the strict equilibrium, and hence two solid outcomes. So here we deviate generically from other concepts, except then from persistence, as I said, and evolution stability also would do that if it's a symmetric game. Now, if you would say that the payoffs for player one were positive, A and B, and those for the other player were negative, then we would have something like a matching pennies game, and it would have a unique mixed equilibrium. And its index will be +1 because if there's one equilibrium, it must be index +1. So we have one game block at the full game, so to speak. So that doesn't say much, but the outcomes, there's only one outcome, one solid outcome. Then one can go to 3x3 games that are coordination games. Yes.
So why is there only one solid outcome? I guess it's the mixed equilibrium, but how did you get the reduction from all these pure strategies that are in the block to this one outcome?
If you look at the case with negative numbers A, B, and so on, for the other player, for the second player, but positive for the first, then it is like a match. Think of the matching pennies game. Okay, then there is only one game block, namely the full strategy block. Man can't get rid of anything there during to this definition, because the mixed equilibrium has support on all strategies, right? So we cannot get rid of anything. So we only have one, and then we ask for for a solid outcome, which is a non-zero index component in the block, and there is only 1 point. It's a singleton. So that we get right away.
Oh, I see, because the outcome is defined as the component within the block.
Exactly. You ask for you decide on. We look for minimal game blocks. Here's only one. Okay, and then we look for natural components in there, and we see, are there any ones that have non-zero index? Right, and there is only one here. Now, if we take a 3x3.
A very stupid question. I'm very sorry. So I understand how you define a game block. Can you please remind me what a minimal game block is?
It means that it is a game block and it does not properly contain any game block. You know, imagine that you have one game block is a full strategy space. So say a big game. Maybe there are a bunch of different other games blocks in that game. Then we would say that the full strategy space is not minimal.
Okay.
And this is finite. Since these are finite games, there will exist at least one minimal game block.
Okay.
Yeah. Okay. So let's take a 3x3 game. This coordination game, I assign now positive payoffs to all the diagonal entries. Now there are 7 Nash equilibria here. One can see 3 strict, of course, to play each of the strict equilibria, but there is also 3 pairwise mixed equilibria to randomize between, top M for the one player and LC for the other, and that is like then a 2x2 coordination game, right? And they will have each of them will have index -1, and there are 3 of them. So now we have 3 plus and 3 minus. So then the remaining equilibrium, which is to fully randomize over everything here, must have index +1. So there is a candidate here, index +1, which we find is very unstable dynamically in any setting. But we have only 3 minimal game blocks and 3 solid outcomes, so that is our prediction. But this will then differ from, for example, sustainability, which will accept the fully mixed equilibrium. And here is now a little vector field, a replicator vector field. If we say that we take a single population replicator on this and we assume symmetry, so the same payoffs for both player roles, we have the vertices are the strict equilibria, and you see the little arrows, they lead to them. So these are attractors. On each edge of the triangle, there is also mixed equilibrium, and that is unstable on that sub polynomial, so that they lead away from there, as we know. And there is also the completely mixed equilibrium, which has no stable manifold converging to it. If you see, everything goes away from that, while the ones on the sitting on the edges, they exist at least one stable manifold that goes there, right? Okay, so this just says our solution concept says the only robust predictions or solid outcomes are the vertices. Okay, despite the fact that the one in the middle has index +1. And another example is the prototypical forward induction example, where you have an outside option, right? There is a player 1 who can choose A, B, C, where C is an outside option and gets payoff 2, or else enter into a battle of the sexes with player 2 with payoffs 3 and 1. Right, and there are 2 equilibrium components to such games, and one is the forward induction singleton, which says go in there and play AL, the best equilibrium for the guy with the outside option. But there is also an outside option component, which is to stay out and believe that the other player will play R with sufficiently high probability. So you want to stay out. Now, this forward induction solution then is a strict equilibrium and has therefore index +1. And therefore the second component must have index 0. And we don't allow for index 0 for components when we talk about stable outcomes. So we have one unique minimal game block, namely the forward induction solution, and that is the outcome. Okay, but now one can make it more complicated. And this is Hauck and Herkens have a beautiful paper, as you remember, many years ago, when they looked at outside option games and forward induction. And here they have one where the outside option now is D for player 1, that can obtain 3 for sure or interact with the other player. And if you look at the top upper corner there, it's 6, 6, and 2, 2. That is like a coordination game between them. It is. I may have been wrong here in the numbers. I'm sure I did it quickly. But, okay, but so maybe it should be double checked the numbers. The idea here is that this will also have two components. One is forward induction, that is to go in there and place and randomize, and the other one is the outside option component. Now, when one can calculate things here and find that the index for the forward induction solution, the singleton there, is -1 in this case. So therefore the outside option must have +2. So none of them has +1. So this is different from the other example. Now, to get a minimal game block, one can drop strategy C for player 1, and it contains the support for both. So that our solution concept admits both the outside option here and the forward induction solution. And we find that I would say I would be agnostic for such a relatively complex game. It could maintain that the people don't dare to enter, they play D. This is indeed what what sustainability in the definition of Govindan and company does. It says that that's the only solution for them that's sustainable if we apply to that example. But I mean, we have to leave this to us. You know, the analyst has to judge here, but we accept both. So there are two outcomes here. Now, if we take the Beer-Kish signaling game, the classical testing ground for many solution concepts, Cho and Krebs, there is an intuitive component and a counterintuitive component. In the intuitive, the potential entrant or the signaler signals some strength and so on, and that component then has in +1. There is one counterintuitive, which sounds strange, but is actually an extra ground component, and that will have index 0 here. If one takes index again, it takes the intuitive component here, like it did the forward, like the forward induction component in the simple game, and it allowed also the outside component in the more complicated outside option game. So I hope this gives you some flavor how it is done. To look at subsets of pure strategies, see if they are game blocks, and then look at what are the set of Nash equilibria in those, and figure out the index, and then that's it. Now, I will try to economize on time. My clock is something like, I have something like 12 more minutes to have for the full hour, is that right? Okay, so I will now walk through these aspects. We had invariance, backward induction, and robustness, and I will briefly talk about them. And the most involved, I think, in some sense, is backward induction. So I will do that first. So we do have Selten subgame perfection, and then the refinement of sequential equilibrium that we all know. But then we also have quasi-perfect equilibrium by Erik van Damme from 1980 and 84. A solution concept which I think has been underused. I think it's a very pretty solution concept, except for its name. I think quasi-perfect doesn't sound very good as a selling point. I would rather call them, man could call them robust sequential equilibria if you like. They are like sequential equilibria, but they imply that you never choose conditionally dominated strategy, which you can do in sequential equilibrium. And sequential equilibrium, I think, has a flaw, that is that it separates belief formation from optimization. So we separate looking for consistent belief systems and go to the limit. And then we look at rationality and continued play. And as we know, there are examples where this is becomes very strange in some games, while the Van Damme's idea is to do this in one at the same time. So you think of players, and then you think of there are some information set, and you ask, what would I do if they didn't play exactly that way up to this information set? It can be an information set off the path or on the path. And then you want to say, I stick to my strategy still, right? So it is not just say in the limit of those B, when they go, when the perturbations go to 0, that then I'm happy. It says that actually for small enough probabilities of doing something else, I'm still, if people might do some other things, I'm still happy with what I'm doing. So I think some of you may know this concept, but I think it's quite important.
Can I ask one quick clarification? Isn't that also the same as, like, say, extensive form Trembling perfection by Selten?
No,
not
it's
quite
different.
So like
it's different. I can tell you what the difference is. The difference is that Selten, extensive form perfection, assumes that you are expecting yourself to possibly tremble and make mistakes in the future. Here you don't. So in this concept, it says that, okay, I'm playing, I don't know, and it doesn't say if there are mistakes or what they are, but it says that I'm willing to play what I'm planning to play, even if I'm not sure that they will do exactly what they have done, what they should do, the other players. I don't think of myself. And that's why it's called quasi-perfect, because I think that Rainer Selten didn't like it so much. But Erik did this, and he showed that if you have quasi-perfect equilibrium in the extensive form, that induces perfect equilibrium in the normal form. So I think it is actually a pretty concept. It is true, it does not allow for your own trembles. Larry Bloom and a younger co-author, they are working on second-order beliefs that maybe first-order beliefs are that others might do other things, and I have a second-order belief that I might do something else in the future, and one can actually refine this further. But that's quite involved. So let's think about it, that people have strategies that they would be willing also even for some specifications of slightly different play by others. So, and here's this pretty theorem, which says that if you take the normal form and you look for a proper equilibrium, Meyerson, then you draw up an extensive form game, which has that normal form has that normal form. Then that extensive form, there will exist a quasi-perfect equilibrium, which is then in behavior strategies, that induces the same outcome. I think this is a very pretty result. So it was actually quite a surprise, as you know, because it says the normal form is enough to be able to say something about backwards induction in the extensive form, any extensive form actually. And that was believed not to be possible many years ago. So this is a powerful thing which connects then from the normal form and to the extensive form. And this is something we can combine then with what we have. And Klaus has a result, an early result, namely that so that we can connect solid outcomes with quasi-perfection. And this is proposition 4.2 here. So if we look at the extensive form game, and then we say, okay, draw up the normal form, look for a solid outcome. Solid outcome will contain a proper equilibrium and hence induce, in terms of realization probabilities of outcomes, quasi-perfect equilibrium, a robust sequential equilibrium. So that's how we get this invariance across the representations. So you can either start from the normal form and look for proper equilibria, and then you know that in every extensive form game, I will get something that's quasi-perfect by this method. Or you can start from an extensive form game and say, okay, I look now for what are the solutions in this, and then you say, okay, I look at the normal form, and then I look for solid outcomes, and then I go back to my extensive form, and I say, well, that's it. I have a quasi-perfect equilibrium. And it will be invariant with respect to changes of the game. So, and this I will not have time to talk about, but you can think about Elms and Rennie's work on the Thompson transformations that keeps the reduced normal form intact, and that will keep the solid outcomes intact. So actually, it is more powerful than what I've had time to say here. Okay, so a prototypical extensive form game would be a perfect information extensive form game. And if you look at a generic such game, so there's no indifference, but they are distinct payoffs and so on, then it has a unique solid outcome, and that is the subgame perfect equilibrium, the unique subgame perfect equilibrium. So it agrees with that in those games. And here comes a methodological observation, which I think is important. So we say that in, for example, the centipede game, the unique solid outcome is unique subgame perfect equilibrium, namely that the first mover opts out. Now, one could say that if you take it seriously and you say we look at subgame perfection, that means, or sequential equilibrium, it says players along out in the tree, although they have seen what player 2, what player 1 has done earlier, and then player 1 later on will see what player 2 has done, they should still insist on the subgame perfect equilibrium, right? But this doesn't say that. It just says that the outcome is robust. So it could be that they reason. We don't know how they reason. We don't have to force them to say that how they reason in the game. We just say that outcome. So it's a whole range of different strategy profiles that could be compatible with that, including, but always including quasi-perfect equilibrium, hence a subgame perfect equilibrium. So it insists on that. So, and I would think it makes sense. I would think if such a game, Centipede, would play recurrently in some population, and people get used to play it, and I think there is laboratory evidence for it, it would kind of unravel. In the beginning, maybe they play along, but they play shorter and shorter and realize that. So I think it makes sense. I hope you think so too. Okay, so it is consistent with a form of backwards induction. Is that okay? Now invariance. So here is a statement of the basic invariance property. Let's look at the block in some finite normal form game. And let's look at the player who has some strategy S bar I, player I, which is not in the block. Now suppose we delete that. What happens then to the block? It was a game block from the beginning. Will it also be a game block after we have removed that strategy that is not in the block? Well, that is true if that thing that we removed is weakly dominated strategy, or strictly dominated, of course. Or else what we took away is something that is equivalent to a mixture over other strategies available to the player. Or there's a payoff equivalent other strategy. It doesn't matter if you take it away or not. So you can go to the reduced normal form without problem. Or else if that thing that we took away is not the best reply to any strategy profile with support in the block. Okay, so these are invariance properties. So one can add or remove weakly and strictly dominated pure strategies. It is invariant across games, which has the same the same reduced normal form. So we can change the extensive form by the Emerson and Rainy transformations, and it doesn't change anything. And we can take away things that are not best replies. So this is invariance. So it holds for a whole family of extensive form games as related to the normal form, and so forth. Okay, so now the final thing to say here, which I will go in any detail, that's robustness. And we had already robustness in the sense of quasi-perfect equilibrium, right? Because solid outcomes induce such, and they are robust to players not believing for sure that others are playing exactly the behavior strategy in question. They can have beliefs that differ, right? So it's robust in that sense. It's robust to players not believing with 100% that others are playing exactly according to the equilibrium. And that is then, as I said, implies actually perfect equilibrium in the normal form. Okay, so it has that robustness, but another robustness is the analyst. We don't know exactly what exactly are the payoffs. We sit there and do an empirical model of something, and we try to estimate von Neumann-Morgenstern utilities or Bernoulli function values and so on, and we get some numbers. And then it would be good to know if it is very sensitive to misspecification of payoffs. So here's a result where we thank Bill Zame for helping us. We got stuck and we contacted him, and he's very clever at these things. So after some time, we could together solve the whole thing, and he provided a way of proving this, which says the following, that generically, the correspondence that takes payoff assignments at the end node of a given extensive form game and say, given those payoff assignments, what are the minimal game blocks? What are the game blocks in general? And also minimal game blocks. That correspondence is upper and lower semi-continuous and even constant. So as you move around and change payoffs, most of the time nothing happens to it. So it's kind of a block valued thing, right? And the set of exceptions where it does change has lower dimension than the space of payoffs. So if the notation here is that little n is the number of players, W is a set of plays of the game, which can be large, millions, and the number of plays. So you take that space, and then we say we can assign the numbers there. These are the payoffs. You know, for this play, how much do we value this with different n players? So if one looks at all those possible payoff assignments to the given extensive form, one can say that one can divide that space, that whole Euclidean space, into finitely many disjoint subsets. U0 is this exception set. So that's a closed lower dimensional semi-algebraic subset where bad things can happen. The rest is divided up into finitely many subsets. And now the correspondence that we have that says, okay, give me these game payoffs and I want to calculate game blocks, it's constant on each of those subsets, UH, when H is positive. So there's the exceptional set is low dimensional, so hence it doesn't exist, so to speak, in terms of empirical. If you would draw raw data and you would find numbers and you measure them carefully. So this is robustness with respect to the analyst tools. And computation. I will be brief here, and we are not specialists on this. There are lots of people, smart people doing in computer science that work on games and have algorithms for all kinds of things. So what we did is we looked for algorithm for generic normal form games. So these are not what we are basically interested in. We are interested in generic extensive form games or any extensive form game. But for this algorithm to work, we apply them to a domain where they do work. So we take regular normal form games in the sense of Harsanyi and so on. So it has to do with, this is a generic class. So almost all games are generic finite games. It means that the Jacobian essentially at the fixed points is non-singular. So this can be done, and Harsanyi suggested that, and this has been developed by people. Now, if you do this and you look at generic normal form games, perfection, properness, statistics brings you nowhere, right? They have no cutting power at all. So all Nash equilibria, all components meet those criteria. but not our game, as you saw, because we could say in two by two games we could have, say, 3 Nash equilibria, and it will rule out one of them, for example. Now, so what we did then, we're running computers, and this is one of the tables we have. So we looked at the number of players, little n, and for each player, suppose they have m pure strategies. Suppose you choose, a 3-player game where each player has 4 pure strategies. Now draw randomly, uniformly on the unit interval payoffs for those strategy profiles. So this is normal form analysis. And then we ask, how many solid outcomes are there? That's a number without parentheses. So that would be then 8.53, that if it is 3 players and they have 5, let's say, pure strategies each, remember that the set of Nash equilibria is astronomical in these games. I mean, it's millions. I'm sorry, I shouldn't, that was false what I said. It's not millions in this example. It is easily, I mean, rather low numbers, you get enormously many Nash equilibria. So we are interested in how many are solid outcomes. And in this case, it is 30%. So we have 8 outcomes. Expected number of outcomes that are solid is 8, and that corresponds to 31% of the Nash equilibrium outcomes. And the higher up one goes here, the lower gets the numbers. Okay, and one gets up a little bit in this ladder, the numbers is very high for Nash equilibria, and it doesn't increase as fast at all, it seems, for solid outcomes, because we look minimal blocks, and that somehow rules out some of the combinatorics. Because if you find a minimal block, you don't have to look at bigger blocks that contain it, right? So you get rid of those. Do you see what I mean? So you start with the game and you look at the smallest blocks, singletons, and then you look at 2 by 2 and so on. And once you find them, then you can rule out bigger blocks that contain them. And that makes it actually, the cutting power is quite strong, and it's also computationally possible to find them. Let me find, now this is a learning and evolution in games. Let's say something about evolution. So let's look at any block of pure strategies, and let's look at the phase or subpolyhedron that's spanned by those. So this is when people use mixed strategies with support in those population states, where people use only pure strategies in that subset. And then let's look at the class of dynamics that Klaus Ritzberger has analyzed with de Michelis and so on, namely that the time derivative, the change of the population state, is given by some vector field function f, such that if you are at a Nash equilibrium, nothing happens, so it's a rest point. Every Nash equilibrium is a rest point in the dynamic. It's Lipschitz continuous, so we can actually have unique solutions to the system, and it doesn't point outwards, so you don't start to get negative probabilities or some probabilities that are more than 1. And also, it's connected to payoffs in a rather weak way, namely that it's pointing in the same direction as the gradient of payoffs. So it doesn't, the angle is acute, so that the inner product is non-negative. Okay, so it doesn't point in the opposite direction. And this is true for almost all dynamics that have been used in evolutionary models. And then one can take results from Stefanos and Klaus' work and obtain that if you have a block such that the polyhedron spanned by it, subpolyhedron, is asymptotically stable in some such population dynamic of this wide class, it must be a game block. Okay, so it has to do with the index +1, some. It has also to do with the case that these are game blocks, they don't, they respect Nash equilibrium components. If you have blocks that don't respect equilibrium components, it cannot be asymptotically stable, because then there will be a component that has some Nash equilibrium in the block, so to speak, and some outside. And the vector field doesn't move, it's 0 there, so it doesn't move. So if you look for asymptotic stability for such subsets of this type, you can, without loss of generality, say, well, we have to look at game blocks. And that connects it then with our solution concept, which is more recent on invariance and robustness and so on, backwards induction. So that is necessary, but not sufficient. The sufficient condition Klaus and I developed in 1995, namely that blocks of strategies, sufficient condition is that they're close under better replies, that they contain, you look at population states in such a subset, and you ask, what are the pure strategies that give me at least as much payoff as the average now? And they should also be in the block. And one can show that these are the asymptotically stable blocks. So that's a sufficient condition. So there are connections. But I broadly speaking, it seems that for evolution, one may have to take a larger box than for this more rationalistic criterion we have developed. So allow for that it swings out sometimes, the dynamic outside of Nash equivalent components, for example. I think it would be fun to work more on this connection. But I like the idea of having connections between what evolution says and what more standard or rationality-based concepts say. Concluding comments then. So we have a concept that we argue has strong invariance, robustness, and backward inductive properties, and it permits computation, at least for not too large games. And then I would like to add then that sustainability, but this will be very brief. And this is a notion that Meyerson suggested. He wanted to think of solutions to games as predictors of what could happen in a population that have a possibility of learning about the interaction. And this happens, and you hear about others doing this, and you don't want to deviate. You don't benefit from deviating from that. Something like that. And this was elaborated and formalized by Joseph Hofbauer, who suggested, let's look at let's look at regular Nash equilibria. Okay, so it's a non-generic property. And then he said, it seems that they should have index +1. That should be necessary and sufficient for this. At least it seems like that. This von Stengel and Schemde, they proved this and could extend also proof from 2-player games to arbitrary number of players. And also Govinda, Laraki, and Pal developed the concept. So what we did then is that we took their definition of sustainability and we said that let's adapt it to a block property. And then we can show that if you want to look for sustainable blocks in the sense of sustainability that they have formalized, you have to look at game blocks again. So game blocks are candidates both from the evolutionary perspective and from the sustainability perspective. Sustainability is something can be a social norm, essentially. Yes, ladies and gentlemen, that's the end of my presentation.
All right. Thank you so much, Jörgen. Let me stop the recording and then we can proceed with the Q&A.